Yeah, so as a mechanical engineer, I would like to talk a little bit more about the concept of our robot and how it's different from the Intuitive's Da Vinci system. As Tom said, we started out as a collaboration between the Technical University and the University Medical Center. And now we are, after we developed the first prototype, we are developing it within a startup company called Microsurgical, which also has a website which you can check to see our updates. So what we want to do, and what we only want to do, is to enable the next step in microsurgery by offering enhanced precision. Nothing more, nothing less. And we do that by first offering precision to solve unmet need, such as this can be seen in the lymphedema. Then as a next step, we want to enhance the clinical efficiency by reducing complications. And as a third step, we want to improve availability. As Tom said, our vision is that every microscope can be equipped with a robot, because as you can see here, you're already enhancing your vision, but you are not enhancing your hands. So this is how Da Vinci is set up, and you see that the whole OR has to be changed. But what if we can develop something that looks like this? So we have only a small robot, the rest of the OR stays the same. We have the same way of operating, and the only thing that's added is a small and compact robot. And this is what it actually looks like. So you see the surgeon using the microscope, which is an old model, but it has all the enlargement, like 25 times, 40 times. You can just use it as you are used to. We have these small compact arms which weigh 1 kilogram each, and they are equipped with the original instruments, so you can attach your own instruments to the robot. The intended use is only for soft tissue open procedures. Our device is limited. It can only apply a force of 100 grams, so this means it's inherently safe. It cannot really damage a patient. It's only meant for microsurgery and for microvascular anastomosis. So this is basically the concept in a nutshell. We use the existing microscope, we use the existing instruments, we add a robot, and then we get this. Here you see a video of the first prototype. So the surgeon has a left and right hand joystick. We can apply a motion scaling of 1 to 1, which you want to use when you want to do fast movements. But you can also switch to a more precise movement when you apply a motion scale factor of 1 to 7, 1 to 10. It's basically just a button that you can turn. When you want to be more precise, then you turn up the motion scaling, and when you want to be more fast, then you turn it down again. So here you see the large motion scaling, 1 to 7. Skip ahead a little bit. Right. In the next part, you see how we can swap the instrument. So now we are holding a needle holder, just a normal one. You can take it out, sterilize it, put it back in, and then you can immediately continue the operation. And here you see how we have been performing anastomosis on the 2 mm silicone vessel. So this is a 25 times magnified view through the microscope. As Jesse already explained, normally you would see your hand tremor a lot. In this case, you see that it's really stabilized. What you do see is that it's still slower than the hand. So this video is not sped up or anything. This is the actual speed. And you see that it takes a little bit longer, and we're working on that. This is our development roadmap. So last year we have been doing usability tests, and we have done the pilot tests on rats. At the beginning of 2016, we are coming out with a second version of the model, which we are going to use in preclinical trials, and then do our first test case on human. And after that, in 2018, we hope to have the device fully functioning and finished, and we can make it a commercial product. So what we are doing now is just gaining clinical evidence by doing tests on artificial tissue and also in vivo, and also expanding our network. So we are talking to clinical partners, industrial partners that can produce the robot, patients, but also health insurance companies, which is a big issue here in Europe. So with this network, we can develop faster. Now the next step we want to do is to translate our first prototype on the left to a Gen 2, which you can see on the right, which can be used as an investigational device. So we can offer it to other hospitals that can use in clinical trials. So the first prototype has proven that it's portable, it's easy to use, it's just generally safe, and we have used in several tests that you can see there. The next one should have improved accuracy, improved range of motion, as Don already described, and also we want to make it more efficient. So we want to reduce the time. We want to make it as fast as you can do by hand. And then we can use it to do super microsurgery. We have already been able to suture vessels of 0.5 millimeters. With this system, we hope to go even smaller to 0.1, 0.2 millimeters. We have already built a test setup which has proven that the accuracy is 4 times improved compared to the first model. So we are going to reach that spec. Also, the range of motion has been dramatically improved. We have basically unlimited range of motion now. As you can imagine, by a sphere that can be thought around the operative site. And in the beginning of 2016, we will have the full system ready and working. So for next year, RAMSES 2016, we hope to present to you the results of the second version, also some preclinical trials, and we will hope to make a start with the first test case on human. So preclinically, that means that we are going to do super microsurgery, try to reconnect lymph vessels to veins. The test case on human will be started at the academic hospital in Maastricht in the Netherlands, but we are looking for more clinical partners that can also investigate other applications, and we want to publish in the next year. We haven't done any publications yet, but we want to do some publications in some renowned journals. Thanks for your attention.